Okay, now I'm going to help you solve 6.64. We have this circuit here. Basically our emitter, it doesn't have a emitter resistance, right? So the emitter up here, we just know based in the circuit that VE is actually 3 volts, right? Because this voltage source is connected directly to the emitter, right? And remember, this is an NPN transistor. Sorry, PNP transistor. PNP. Okay. Because of the arrow here pointing inside the BJT. So we have an emitter current flowing here. We have a base current flowing here. And we have a collector current flowing here. And in this particular problem, we know that beta is 50. The common emitter current gain is 50. And we want to design the collector resistance so that VC is equals to 2 volts. Okay, we can start, and after that we are going to change the value. So once we know the value of RC for this to be true, we are going to change the BJT. Suppose we change for a BJT that has a beta equals to 100 now. What is the value of VC? What's happening to the circuit once we change the transistor? Okay, so our first assumption, again, it could be operating in the active mode region, and for that we know that the voltage VEB for the PNP, so this voltage here, is 0.7 volts, right? And because we note this condition, right, let me write it here. So VEB is equals to VE minus VB, which is the same as 0.7 volts. We know that VB in this case is equals to VE minus 0.7. Okay, and this analysis, it doesn't depend on the value of RC. So our VB here, no matter what's the value of RC, it's going to be VE, which is 3, right? The minus 0.7, which gives us 2.3 volts. Okay, so this voltage VB here that we see exactly at this node here is this value here. So let me put it in blue here. Now, a second assumption, or a second verification step to actually prove that we are operating in the active mode region is that VEC. Okay, so let me pick another color. VEC should be greater than 0.3, okay, volts. And because we are forcing VC to be 2 volts, this condition here is satisfied because we get VE minus VC, okay? VE is 3 volts up here, and we want to calculate RC, so we get 2 volts at VC at the collector. So this 3 minus those 2 volts gives us 1 volt that is greater than 0.3 volts. Okay, so we are going to calculate RC in order for that to be true. So it's okay to assume that the BJT is operating in the active mode region. Okay, now since we know VB, okay, so we know this potential here, VB equals to 2.3, right? We can calculate the current IB that's flowing here, because that's the current that's flowing through this 100K. So the current IB is going to be equals the voltage, 2.3 volts at this terminal, right? Minus the voltage at this terminal, and again this is grounded, 0 volts. So it's minus 0 here, divided by 100K. And this gives us an IB of 23 microamps. Now, because we know IB equals to 23 microamps and we know the value of beta in our first case is 50, we can calculate the current at the collector, right? So the current at the collector here is going to be equals to beta times IB for the active mode region. So this gives us 23 microamps times 50, which is an IC of 1.50 milliamps. Now, if we want to force this voltage VC to be equals to 2 volts, we need to make sure that the voltage drop across this RC here is actually those 2 volts, because this terminal here is grounded. So we need to have this voltage drop of 2 volts here in order for VC to be equals to 2 volts. So if we calculate that, we can basically define the value of our resistance RC as the voltage that we want to have at VC, right, divided by the current IC. So it's 2 divided by 1.15 milliamps. And this one here gives us 1.74 kilo ohms. So if we use this value here of 1.7K in this resistor RC here, we get those 2 volts that we want for this particular BJT with a beta gain of 50. Okay. Now we have selected our collector resistance, and the second part is, what if we change beta in the circuit? So what if we change beta to be 100 now? What happens to VC? Now if we change the value of beta, and remember that the current at the base here, okay, it doesn't depend on the value of the RC, right? So we still have IB equals to 23 microamps. And if we calculate IC using this beta here, this new beta, it gives us 23 microamps times 100. And that's a current IC of 2.3 milliamps, right? So it's greater than, it's 2 times the value of the IC that we had previously. Now if we know that this IC is flowing through this resistor here, we can calculate the new value of VC, right? So let's do that. VC is actually, because it's grounded, it's just RC times IC, and this gives us 1.74 K ohms times those 2.3 milliamps, and this gives us a VC of 4 volts. Now this 4 volts, we have changed the value of VC, and we still need to verify if this VC equals 4 volts, it's still making the BJT operates in the active mode region, right? So how do we verify that? So one of the conditions is that, let's go back here. So we need to have VE, right? VEC greater than 0.3 volts. So let's verify that condition. We know, right, because The emitter here is connected directly to 3 volts, so we know that VE is equals to 3 volts. And if we take VEC, right, for the BJT, so we need to verify VEC, it should be greater than 0.3 volts. So VE minus VC should be greater than 0.3 volts. Now, if we take VE equals to 3 and VC equals to 4, this condition here, it doesn't hold, right? Because we get minus 1 greater than 0.3, and that's not correct. So indeed, it's not, if we change the transistor from the transistor with beta equals 50 to a transistor with beta equals 100, based on the selection of RC equals to 1.74 kilo ohms, the circuit, it won't make the BJT operates in the active mode region. So if it's not operating in the active mode region, we can assume now that for a second analysis that the circuit will actually operate in the saturation mode. And for the saturation mode, we know that VEB is 0.7 and VEC, so this voltage here, is a saturation voltage that's equals to 0.2 volts, right? And if we know that the voltage at the emitter is equals to 3 volts because it's forced, right, by this voltage source of 3 volts, we know that VE saturation is equals to VE minus VC saturation, right, which is equals to 0.2 volts. Now we know VE, we can calculate VC. So in this case, VC is equals to 3 minus 0.2 volts. This gives us a VC of 2.8 volts. So that's our value for VC, okay? Assuming that this, with this new BJT of beta equals to 100, remember beta equals to 100, the circuit is actually operating in the saturation mode. But let's verify if the circuit is actually operating in the saturation mode by verifying the conditions for saturation mode again. So one thing is that for the saturation mode, we need to know that beta forced, okay, is less than beta, and in our case 100, right, because that's the new BJT that we inserted in the circuit. Now to calculate beta forced, we need to know the new values of IC and IB. Now one thing that we need to remember is that IB, it doesn't change here in this circuit if we change the BJT. It keeps at 23 microamps. Okay, if you go back in the video, you see that the current at the base, it doesn't depend on the value of RC. So we know IB, but now we need to calculate this new value of IC based on this value of VC that we just calculated, right? So we need to define this current here, IC, again for the new BJT. And this current IC, we know that is VC divided by RC, if you want to be more precise, minus 0 volts because it's grounded here, right? So it's this potential difference here across RC. And this gives us an IC that's equals to 2.8 divided by RC that we selected before. So it's 1.74K. This is volts, this is ohm, and this gives us 1.6 milliamps. If we calculate beta forced is just the ratio of the collector current to the base current. And this gives us, with IC equals to 1.6 and IB equals to 23 microamps, it gives us a beta forced of 69.96, which is indeed, so let's approximate by 70, less than 100. So this value here of VC is actually the value of VC when we change the BJT to 100 for a BJT with a common emitter current gain of 100, because this condition here for saturation mode holds.